All right. If I'm not mistaken, it's time for us to start. Now, last week, you had a visit from one of my good friends, Guo Fang'an. Oh, come in. Now, Fang'an is a good mate of mine. When I first started at the NCHC, I was the only person in the entire government lab doing GPU. After I got some GPU codes running, the government decided to give me one employee, Fang'an, and we went on to do some very, very special codes at the NCHC lab. He's a very funny guy. Did he speak Chinese or English while he was here? Yeah, I was pretty sure he would. He's not a... There's a reason I can speak Chinese. But he's a pretty good guy. I'm hoping that he gave you a lot of information about solving that advection diffusion equation on the GPU. But you guys should already have an idea about how to do that, because we've been looking at that for a while now. But nonetheless, we might have a chance to go over that. But that's not what we're doing today. Today is going to be a big day, because we're covering advanced memory allocation on the GPU device. So until now, all of the memory that we've been using on the GPU has been register memory, which is memory that we store, that we create in our kernels. But the big one is global memory. Every time we use CUDA-malloc, we're using global memory. That's good because the global memory on the GPU is large, lots of it. The GPU you're using, there's 6 gig of it. But the problem is, global memory is very slow because global memory is stored on the chip. And we can see that. Today, we're going to look at several of the other memory types that we use in the GPU to make things go faster, because global memory is just too slow for most of the applications we do. If we want to speed up our memory access, we need to take advantage of the memory which is inside the GPU chip. There are 3 types of memory that are inside the GPU chip. As a matter of fact, 2 of these don't exist entirely in the GPU chip. It's a bit of a trick. The first one does. So we're going to do shared memory. Shared memory is a special type of memory that's quite a large chunk of shared memory available in each streaming microprocessor. And we're going to make use of that one. After that, we've got constant memory and texture memory. These are very special types of memory which are read-only. So Yoda Shahol, sometimes when we're running a calculation, we have data types which do not change in time. We can put that information into either constant or texture memory, and we can use these memory types to speed up our calculation. But more or less, the most interesting ones of these are shared and texture. Come on, computer. Shared memory is the first one that we're going to start with. Shared memory is good. So, in previous examples, all of them, vector addition, our heat transfer simulations, SOR computations on the GPU, all of these used global memory. And it's really slow. And that's because it's physically separated from the GPU core. This is a picture of a dual GPU GTX 560 Ti. They didn't sell these in Taiwan. They were manufactured by EVGA, which only recently in the last few years started selling GPUs in Taiwan. This card has 2 GPU cores on there. You can see this is a PCB. Here is our PCI slot where we plug it into the PCI. That's power and that's data. We've got 2 GPU cores, 1, 2. So this one card has 2 GPUs inside. Actually, a lot of cards have multiple GPUs inside. The only problem being, in recent years, they haven't released any good ones. But, man, why am I circling that? There we are. Yes, here's the GPU core. Inside the GPU core, we have the on-chip memory. That's shared memory, constant memory, texture memory. Inside that off-chip memory, on the outsides here, on the outskirts of this board, we have our global memory. So if we want to transfer information from our GPU core to and from global memory, we have to actually physically make it travel from these registers, these DIMMs, through our memory controllers back to our cores, which is why it's so slow. It's no good if we're going to go really fast. So on-chip memory, because it's on-chip, we don't have to worry about memory controllers. We don't have to worry about the physical time it takes to move information between chips. It's very, very quick. Off-chip memory, because we have to manage it and move it, it's a lot slower. On-chip memory is about 150 times faster than off-chip. So if it was 2 times faster or 3 times faster, I wouldn't teach it to you. 我就不会加，因为没有用啊。But 快了150倍, that is some serious performance increase. And so it means I have to teach you basically. So it sucks to be you because now I have to learn something more. But that's all right. Let's have a look at this extreme streaming multiprocessor. That's SMX. I believe that's a Fermi. If you have a look at all the different types, here's the old SM. That's from anyway, it doesn't matter what GPU. What do we have here? We've got a whole lot of cores. We've got some double precision cores, but down the bottom here, we've got texture cache, which is texture. We've got shared memory, and we've got some constant stuff as well. Let's can we zoom in on some of this? Yeah, look at that. This is a shared memory you want to have access to when I say shared memory. So this 64 KB of shared memory, there's 64 KB in this device across all of our streaming SMPs, SMXs. So all of the cores here, all of the cores in any single SMP or SM have access to this shared memory. Now, if you remember, when we pass blocks of threads to the GPU for computation, all of those threads are executed within the same SM, within the same streaming multiprocessor. That means while those threads are running, they all have access to this shared memory. That means they can share information through this memory. That's why we call it shared memory, because we can share that memory across the threads in our blocks. But different blocks are executed on different streaming multiprocessors, which means one thread from one block cannot see the shared memory from another thread in another block, because they are physically computed on separate SMPs, physically computed on different streaming multiprocessors. So shared memory can only be seen by threads at the same time in the same block executed on that streaming multiprocessor, which means the lifetime of this memory, the lifetime means the time available for us to use this shared memory is basically the lifetime of the block. As long as we have blocks of threads running on this thing, then we can use it. Once the the block of threads has finished computing, then that block of threads is shut down, that work is cancelled, and this disappears, essentially. So let's have a look. Here are all the different memory types. We've used this before. Register memory, that's on chip. Every time we create a kernel, and we might say, is that the GPU, please? All right. If we have a kernel, very good, and we say int I equals thread idx.x. For fun, let's say we don't have any blocks. This variable I is stored in register memory. That means it's a small variable, we don't have a lot of memory available in our registers, and when that thread is finished, when this thread is finished its computation, that I disappears. So that's why we say the lifetime of variables like this is the scope is one thread because each thread has its own I variable because each thread has its own thread idx.x and its own block and dim. So the scope is one thread and lifetime is one thread because once this thread is finished computing its work, it's gone. Now, we've used global before as well. Global is off chip. It is read-write. Every thread can see global memory, and the host can see global memory. We can't allow the host to use global memory, but it must be able to access it because it does the memory copies to and from the device. Lifetime. The lifetime of global memory is as long as you want it to be. 如果你忘记写 CUDA free, it is forever. I'll kill you guys if you do that. Your global variables should be freed at the end of your program execution. So that's why we say host allocation. Host allocation, if you don't free the memory yourself, I will allocate you to a grave somewhere. All right. Global, we've done before. Off chip, painfully slow. Today we want shared. Shared is on chip. And A for it's not cached. It's not applicable. And we'll explain why. It is read-write. All the threads in one block can see that shared memory because every SMP streaming multiprocessor has a section of shared memory, and all threads in a block run at the same time. So all threads can see shared lifetime, however long all of the threads in that block take to run. Once all of the threads in that block have finished their execution, then that memory is dead. It's automatically erased and reset for the next block of threads for it to complete on. So shared memory is shared by all of the SPs, streaming processors, inside our SMP, our streaming multiprocessor, or just SM. Since all blocks of threads are performed at the same time on the same SM, then all of the threads can see that memory. So that's very, very convenient. That's why they call it shared, because if we choose to use this memory, that means that not only can each thread see its own section of shared memory, it can also see any section of shared memory that is accessible by any other thread in that block, which makes it very, very useful for us. Where is this going? So, you know, this, I don't know what you think that's a picture of. That is a picture of a block of threads. All of those blocks of threads, well, see, all of those threads inside that block, are executed on that SM. They're all executed at the same time. A different SP will control each thread, perhaps, but because they're all executed at the same time, they all have the same access to the shared memory. Yeah. I think everything that's written here is basically what I just said. So if you don't understand what I'm talking about, there's the information. There's a reason why we use shared memory. Because shared memory is on chip, and it is so physically close to our SPs, the number of cycles required to access information from shared memory is only 4 cycles. Whereas if we wanted to access information on global memory, we needed 600 cycles to get that information, simply because it's so far away. So shared memory is a lot faster. So what does this mean for us? It means that, well, we have 2 opportunities. One, we can use this shared information, shared memory, to allow threads to exchange information. That's not a bad idea. But actually, that's not all we can do. If we want, we can copy information from global memory into shared memory. Then all of our calculations can use a shared memory because it's faster. And then when we're finished our calculation, we can copy that result back to global memory. 所以这样的话，我们只有看 global memory 的样式。开始的时候，我们 copy 过来的时候 and then when we copy the answer back. So if we want to use the GPU like this, actually shared memory is not being shared across threads. Every thread only accesses its own element of shared memory, but it is fast because all of the data in shared memory is accessed so quickly. So basically the idea might be, today, if we previously used, I thought that was my phone for a second, gosh. If we previously used global, we can stop using global. When we start our work, we can copy the information from global into shared, move the memory from global into the on-chip cache, on-chip shared memory section. Then all of our calculations are on-chip. None of them are off-chip. Then when we're ready, we can copy the answer back to global. Because as soon as our block of threads is finished computing, that shared memory is erased, and we lose our result. So we must transfer it back. The only problem is the size. So obviously the best thing to do would be to copy all of the data from global memory into shared memory and do all the calculations and send it back. But you only have 64 KB of shared memory. Now that's a pain in the neck because that 64 KB in shared is for the entire streaming multiprocessor, SMP. Now, until now, I've been telling you that only one block of threads will execute at once inside an SMP. That may not be true. The GPU scheduling hardware chip may decide that this SMP, having 600 something cores and being really kick-ass, can manage more than one block of threads at the same time. And so we'll schedule more than one block of threads to run on that SMP at the same time, which means that we now have 2 blocks of threads sharing this 64 KB of shared memory. 这个是什么意思 ？You'll run out of memory very, very fast in shared memory. 我们没办法放完全所有的 data 进去那里。到现在有办法，因为我们到现在我们所有的计算都是 toys. We haven't started doing any real calculation yet, but we're going to before the end of this course. If we want to run a real engineering simulation with 10 million cells, 10 million cells will not fit into 64 KB, ever. So we need to find a way to copy bits of it into shared memory. So the best thing to do would be to only copy the parts of global memory that we need for our calculation to shared memory, sorry. And then when we finish, copy the stuff back. Oh yeah, we already know. Shared memory is on chip, global is off. Whoop-de-doo. Keep going. Come on, computer. So, what can we do? Well, we already know that we can't fit the entire reserved variables that we have in global memory into shared memory. We have 6 gig of global memory on the GPU, but we only have 64 KB per streaming microprocessor on, in each streaming microprocessor. So we need to find a way to break the data down. Now this is pretty convenient because we've already found a way to break our problem down. Before I left last week, and I think Feng An might have done the same thing, we took arrays like A here, which might have had n elements inside, and we create 1 thread per element. Did Feng An do the same thing last week? 郭方安他有没有给你看他的 GPU code? 有 Did he use 1 thread per cell in his code? I can see a ball of grass rolling across the floor. I'm pretty sure he did, because I taught him how to do GPU, and I think he's still doing the same thing. I might be wrong. I'll go on. I can see the video, right? You got it on video, right? 他有综艺让你们拍吗? Yeah. Okay, I'll go find Feng An on YouTube and see what he did. We're going to do the same thing. We're going to say each thread controls 1 element. So we're going to have each thread in each block copy 1 piece of our global memory into local shared memory. So, computer, there's a block. Inside this block there are many threads. If we have 256 threads here, then we're going to control 256 elements of A. So make a thread where truly you get element of A, and we're going to copy that into shared memory. So all of these blocks will copy their own section. Now, this is dangerous. Why is this dangerous? Let me tell you why. Because maybe, 如果我们要用一个分享的方式让 threads 看另外一个 threads shared memory 哪里 we need to be careful because this thread here in the middle 它有办法看左边右边的那个 thread shared memory. That's fine. 因为它在中间 This thread here on the end 它可以看它的右边的那个 neighbor shared memory. 但是左边的在这里 that's in a different block, in a different streaming multiprocessor. He can't see his shared memory. 所以如果我们要用 shared memory 分享那个计算还有 control the access to neighbor data, we need to take应该是说 pay very close attention to the threads on the ends of these blocks. We'll come back to this soon. So, let's imagine here that we have n elements in A. We have 256 threads per block. So our thread IDs will vary from 0 to 255. And each thread is going to copy 1 element of A into shared memory. So let's do that. Come on, computer. So, each thread will copy some information from A. Then all of the calculations will use shared memory to complete its operations. Then once all of the computations are complete, we're going to copy information back. So each thread will then copy its solution from shared memory back into global memory. So theoretically, 其实我们有加2个工作，一个是我们要 copy 那个 global data 到那个 shared memory. 跑计算以后我们要 copy 回去. So actually, you can see here, using GPU, we need to be very conscientious of how we copy data. In this case, we have 2 copies. 我们要 copy 从那个 host 到 GPU, 还有我们抛计算的时候，我们要 copy 从 global memory 到 shared memory. It's easy to do. Luckily, it's much easier than the host device copy. Ah, goodness gracious me. We have to copy it back because once all the threads are finished, the memory is erased. 因为它那个 memory 它要准备有新的 block 新的 threads 过来跑它的计算。So, here's code. I love giving code. If I'm not mistaken, this is code that you can cut and paste. This is not a picture. Am I right about that? Can you guys test? It is, isn't it? I see a smile on his face. I just know that he can cheat now. Be very careful when you copy and paste because Windows formatting is different to Linux formatting. Well, I think everyone here has already been burned by this at least once before. So let's have a look at our global function. We see this global here. We know it's a GPU kernel. I do not have a good imagination. You pick a function name. And we're going to perform calculations with A and B. In this case, B is our answer, A is the data that we need to use to perform our computation. Big I is our thread ID. Little I is basically our global index to our array A. So little I 就是我们以前有学过 little I 就是 blockdim x times block idx.x plus thread idx.x. I know it's a pain in the neck, but one day you're going to have this stuff memorized. Eventually. So, what is our mission here? Remember, we want every thread inside that thread block to copy one element of A into shared memory. And then we will use that shared memory to perform computation. So, how much shared memory do we need to allocate? In this case, blockdim x. We need blockdim x because blockdim x contains the number of threads per block in our problem. But there's a problem here. Here is our shared memory. How do we know that this variable is shared? We write shared. So what does this mean? Does that normally, 如果这里没有 shared, what will happen here? If we don't write shared here, it means that every thread is going to create a variable called A shared containing 256 elements. This is a very good way to run out of register memory. We don't have that much memory in registers. If every thread allocates an array with 256 and we have 256 threads, that means we have 256 times 256 floating point variables inside that streaming multiprocessor. That's very bad, but by writing shared here, CUDA knows all of the threads in this block are going to share the same variable, A shared. So this array here is created once for the entire block, and it contains 256 elements. This must be the same as this. 我们不可以让写 blockdim x.x 在这里，因为这个 size 不会改变. We can't have that as a variable. So, unfortunately, we have to manually type it in. There are ways we can get around this, but I'm not going to go into that. 第一个工作是什么？我们要 copy our variable from A into shared. So, that's what this big I is for. Remember, we have 256 threads. So we have 256 elements in A shared. That's why we use big I here. Because big I goes from 0 to 255. Big I is the thread ID. AI, we're copying our own piece of A into A shared. Little I is the index to our large array. If you want to crash your computer, write little I here. And if you want to get the wrong calculation, the wrong answer, put big I here. Make sure you have your brain turned on when you're writing this code. It's very easy to make a mistake with this. So big I is our thread index. Little I is our global index, and little I controls which section of the array we're copying across. Now we have our computation. 我们的计算就是 A equals A加 square root A. It's a very simple SIMD vector computation. But you can see everything is shared. Square root's a slow function. We could probably speed this up by using an intrinsic function. Once we finish our calculation, we need to ship this back. Remember, our answer is put in B variable. So, and remember, we have to store it in the correct point in B, so we have to use B little I is equal to A shared big I. Again, try to use the wrong indexes in the wrong spot. This is going to fall to pieces. And there's a calculation we're performing. 你觉得这个会变快吗? No. This code is slower. There's a reason. 你觉得那个计算很简单吗? 这个计算太简单了. This computation is too easy. If we had a real computation, then yes, we have a chance of increasing the speed. But in this case, we're just saying A equals A plus square root A. That's no biggie. That's pretty easy. That's only 3 memory accesses. And we actually have to perform memory accesses. The first one, A shared equals A, and then BI equals A shared. We're only making this faster by about 4 cycles, perhaps. So we do get a speed up here, but it's not really worth our effort. One thing that we can also see here, A shared contains 256 elements, and all threads in that block can see the same memory. But any thread in this code only looks at his own section of shared memory. 所以其实它有办法看别的 threads 的那个 index， 别的 threads 的那个 shared memory， 但是它没有看。如果它要看的话 we have another problem. Alright, we're going to talk about that problem soon. Let's have a look at how we declared this. A shared variable in our kernel is declared by writing shared. Of course, just like every other CUDA variable, look, 1, 2, shared, 1, 2. This is not 1 underscore. Every GPU device special function or name always has 2 underscores. So that's how we declare a shared variable. We must set the size manually. I want you to assume. We can make shared memory any dimensionality we like. So shared variables can be 1D, 2D, or 3Ds. Guess what I'm going to ask you guys to do? Nothing you do in this course will be 2D or 3D. 当然，你们会跑 2D, 3D 的计算, but all the data you use will be 1D. So we don't have to worry about 1D, 2D, 3D. In this case, this example is a 1D variable, and that is good enough for us. Now, we have to be careful. Remember, I can't write blockdim x here. It doesn't work because I need a constant, and blockdim.x doesn't fit the bill. In this case, I know that I'm going to call this kernel with 256 threads per block, so I manually put in 256. If you want to try putting blockdim.x in there, knock yourself out. See what happens. Your compiler won't like it. Now, we have a problem if we want threads to see other threads' value of A shared. What's the problem? Some threads are faster than other threads. We have a block of threads. Each block of threads in this case has 256 threads. Some threads are going to be finished before other threads, especially if you have a crap GPU. If you have a crap GPU that has 32 SPs in each SMP, that means if you have 256 threads, you've got bad news. Some of those threads are going to finish a lot earlier than other threads. What does this mean for us? In this step here, we copy A shall I into A shared big I. Some threads will finish this work before other threads do. 所以在它的上面，如果 if we want other threads to use other threads' shared memory elements, we need to make sure that that thread has finished copying the information across. 如果我们没有决定它有 copy 好，那我们就完蛋了，因为它可能还没有 copy. Maybe it hasn't finished copying. Maybe one thread is so much faster than the other threads that every time it tries to use someone else's A shared, it's all 0 because that thread has not had time to copy its value across. Now, for this calculation, it's easy, but if we want to do FTCS, heat transfer on GPU using shared memory, and we want to use shared memory to speed up the neighbor computation, we need to make sure that each thread has copied the information across. So, we can force each thread to wait for all of the other threads before proceeding. This is called a red light, or in parallel computing terms, a barrier. Now, barriers, actually there are many, many different kinds of barriers in GPU computing. This one is a block barrier. We call this function sync threads, which means every thread in every block will run to this point. When it gets to this point here, it will wait until it is sure all of the threads in that block have finished their computation. Once all of the threads in that block have finished their computation, then it will continue. Now, there is a downside. This is like a red light. It means that the fastest threads will have to wait for the slowest threads to finish their work. The downside is, it's like working in a group project. The fastest thread, once it's finished its work, often has the chance to take more work. But by putting async threads in like this, you are stopping that fast thread from being fast. You're basically slowing your thing down, slowing your process down. So we try to avoid using sync threads wherever we can. But in this case, if we want each thread to have access to other threads' areas of shared memory, we must place it in. Otherwise, there's no guarantee it will be ready. So in this case, I've modified my computation. You can see A shared equals I minus 1. So in this instance, thread I also wants to have access to I minus 1 section of shared memory. 如果我们没有放那个 sync threads 进去，那我们就完蛋了. It doesn't work. All right. Let's do it really. This is a heat transfer code on the GPU. It should be very easy to modify this code to do the 1D advection diffusion problem, right? In theory, we just have to add the upwind term. Now, we have to remember, there are some tricks here. So, here is our global memory. I'm going to call that DA because all my variables seem to be called that. We're going to have a block of threads. That block of threads is going to be here. That block of threads will control that section of global memory. The very first thing we're going to do is copy that into shared memory. Every thread will copy one piece. Once that copying is completed, we must wait. We have a red light here to make sure all the threads are finished. Once we're good, we can perform our computation here. So let's say we have a cell I plus 1, I minus 1. Our temperature computation can be performed using these three cells in shared memory. So that's fine. But what's our problem? The problem is this cell and the first cell. If we have the first or last thread in that block, 它没办法看这个 thread， 它没办法看它的右边。这个 thread 它没办法看它的左边。All the other threads are fine. 它们可以看它的机器，都 okay. But these threads, we need to take special exception. So, if we want to write an FTCS code that runs on the GPU, after we've copied the information across, you can see I've got A and B as both shared, it doesn't matter. The new temperature is the old temperature plus our CFL times left, right, 2 of its own, right? So 这个就是 1D heat transfer. Piece of cake. That's that. You should be able to recognize these equations off by heart at this point in time. So, if our big I is larger than 0 or less than 255. That means if we are living in this space, 我们就用 shared memory 就 OK 了。如果没有的话，不好意思，算了，我们可能没办法看左边的还是右边的。Being incredibly lazy, what do we use here? Global memory. You can see here we're using A, not shared A. So in this part of the computation, in the middle, we're able to use shared memory, but the left and right-hand terms must use global. Will this accelerate our computation? The threads in the block are going to wait for the slowest threads to complete before the block of threads is computed. Which means it doesn't matter. It's still going to be about the same speed. These threads are fast, but they still have to wait for those slow threads to finish. So, but still, for very large problems, and if we're careful, we can improve the performance. There are other ways that we can use shared memory to make it go fast. This is just an example application for you guys to look at. So, if we're inside the middle of our block of threads, if the thread ID is larger than 0 or less than block_dim.x, we use shared memory, 100% shared memory. Otherwise, unfortunately, we need to access some of it. I'm particularly lazy here. I could use a shared here. I'm a lazy engineer. So are you guys. If you want to make my code go slightly faster, you can write a shared here. Otherwise, if you wanted, you could use more if statements, but if statements slow things down on the GPU, unfortunately. I'm just showing you this code so you get the idea. We can't forget the last step. This is our new temperature. We need to copy it back to global memory. And then we're done. Of course, we need to do a mem copy to copy the new temperatures over the old temperatures after this is finished. Do you guys really want to see me write a GPU code for 1D advection diffusion? You saw it last week, right? You know, I tell you what, if you guys want me to, I'll do it later. Just for fun. I don't feel like it. Because we've got better things to look at today. Come on. Constant memory. This is a good one. So I just showed you shared memory. Shared memory is available to all the threads within a block. And once the block of threads has finished its computation, the shared memory is reset and set up for the next thread of blocks. But sometimes we don't need that much flexibility. Sometimes we have variables which do not change as our computation progresses. Examples. Let's say you want to do a smoke or pollution simulation in 3D space. 如果你这样算的话, you will calculate the smoke or pollution density. But to do this, we need to know how the air moves, right? The airspeed. Maybe we will perform some other 3D CFD calculation, or we will perform experiments to measure the wind speed. And that wind data we will save or we import into our GPU computation. That wind data is treated as constant because our solver only solves for pollution density, doesn't solve for wind. So that wind data is separate, constant, doesn't change in time. We can store it in constant memory as a way. Now by doing this, it's faster. Constant memory is quick, but the pitfall of constant memory is this. It is not large. What is interesting is that constant memory is available to all threads in all blocks. That's pretty neat. In shared memory is available to all threads within a block. Constant memory is available to everything, but it is small. If you have something small, then you can place it in global memory, in constant memory, without any trouble. A good example is your pipe network simulation. Your pipes network simulation contains information about the roughness of your pipes. Each pipe has its own R, if you remember. We don't have that many pipes. Maybe you'll have 100 pipes or 1,000 pipes. That's still a small amount of information. 1000 R values for your pipes will still fit in constant memory, and those R values do not change in time. So that's an excellent example of constant memory. And constant memory is stored on chip, so it will be accessed quickly. So using constant memory actually is very, very similar in the way we set it up to global memory, but it is faster. To create constant memory, we need to create a pointer to the memory that we're saving in constant memory. We need to use a process similar to memcopy to allocate its value. And then after we've done this, all threads can access this variable without passing it through as a function pointer, without passing the pointer through. So this is pretty neat actually. Now, I call it constant memory here. Some engineers at NVIDIA call it symbol memory. Let's have a look. So here's a code. This code does some simple stuff. I create a function up there. I've got a constant variable called dx, d_x. I place the d there to let you remember that this variable is on the device, just for our reference. And you can see the size is fixed. I don't use CUDA-malloc here. It's a fixed size. And it is constant. Again, there are 2 underscores here. That constant is 2 underscores. So dx is up there. I've also got my test function, which is a GPU device, a kernel that runs there. My function is defined down here. So you can see here my computation is quite easy. I have 200 elements. I have 16 threads per block, and they are going to operate across those 200 elements. You can see this calculation here, we use N200 to share our work. So again, every thread is going to have access to one element of that, and we're going to use that in our calculation. So how do I use it in the calculation? Actually, this A, which is a device variable A, I'm just going to set it equal to this constant, just to check how it works. So this code does, well, let's have a look. Set the number of threads per block, that's 16. Calculate the number of blocks. Allocate dA. We do not allocate dx. We've already done that here. Then I set up hx. You can see here, hx, I didn't use malloc for this either. So that means I placed it on the stack. That is a stack variable. So here, hx is this. Then I use this fantastic function here. We've previously used CUDA memcopy to transfer information from a host variable to a device variable in global memory. We do not want to place our information in global memory this time. We want to place our information in constant memory. And what did I just say NVIDIA engineers call constant memory? Symbols, symbol memory. So, because those funky engineers at NVIDIA have control over their variable names, the function is called CUDA memcopy to symbol. So we're going to take with all memcopies, it's always the same. The first variable is the destination. Then we've got this, and then we've got this. Ibanda memcopy, you might remember, has another thing here. It could be CUDA memcopy device to host, or host to device, or device to device, or host to host. We don't write anything here. We know where it's going. We are copying to symbol. So, after we've allocated hx, I can map it into constant memory by using CUDA memcopy to symbol. Now, we are free to run our kernel function. We pass dA, which is our answer, but we can see here we pass dA as A here. I can use dx directly here. So I'm able to use that constant memory directly in my kernel function. I don't have to pass it through as an argument into my kernel. 所以跟以前的很不一样。以前如果我们要跑什么计算在 GPU 上 need to pass a pointer to that variable. This is global. That constant memory. Why is it global? Every thread in every block can see constant memory. It must be. Otherwise it's not. So, shared memory, is this easy? How do we know it worked? Well, you can see, in this case, I copied dA back over to hx, using CUDA memcopy device to host, and then I print this. 其实现在结果一点无聊吧。It doesn't change anything. Here I set hx equal to this, then I set a equal to dx, and then I set ha equal to dx. So nothing changes. If you really want to test this code, add a 2 times dx here, and this function should double its value. It is very important that we remember that dx constant, we wrote constant up there, which means we cannot change its value once it's allocated. If you want to see it crash, we can try to change its value. Come on, computer. Yeah. Let's do it. Let's change our test function, and we try to set dx equal to a. So, 上面的就是一样, I added the 2.0 there because I was bored. 它的上面, I wrote a new line of code saying dx equals blah blah blah. If I try to do this when I compile my code, my compiler will say error cannot store to pointer that points to constant memory space. I really wish that I could work at NVIDIA and change those error messages. But if I did that, then people would not use my compiler because I would be saying something like, don't be stupid and trying to change the constant memory. You set it to be constant. It cannot be changed. It is constant. That's constant memory. Piece of cake. There's a problem. Constant memory is tiny. Constant memory is small. You cannot possibly hope to put a large amount of anything inside it. If you're doing a finite element simulation requires the volumes in all of the elements. If you have 1 billion cells, that means you have 1 billion volumes. Those volumes don't change as the simulation progresses, so they are constant, but they will not fit into constant memory. So, if you have data like this, data which is very large but doesn't change, I'm afraid that you need to use my good friend here, texture memory. Now, texture memory is designed for games. The whole GPU is designed for games. Everything here is for gaming. Texture memory is really for gaming. They even kept the name because they're not lying. This memory is designed to store textures for your graphics. Now, basically, we're walking in here and saying, GPU, you think this section of memory is for graphics? It's not. And we're tricking it into holding our floating point information. Now we have to be very tricky here. The GPU is going to do everything it can to try to believe that what you give it is a texture. It really wants to have a texture. The GPU does not want to do your computation, it just wants to play a game. So we have to be careful, because when we use CUDA, there are about 30 different types of texture operations, and 29 of them are for textures. One of them is for computing. So the method I'm about to show you is the computing way. If you try to Google texture memory CUDA, I guarantee you will find information about the other 29 ways. But you will not find information about this way. Ask me how I know. I'm saving you guys so much trouble. If you want to try to find out, Google CUDA, texture memory, and see if you can find this information. Guarantee you it'll be on my webpage. So, texture memory is inside our streaming multiprocessor. Actually, texture memory, because we have a requirement for texture memory to be very large, that's why texture memory exists. And when we play computer games, all of the graphics information goes into global memory because there's a lot of memory there. What is texture memory actually doing? Every streaming multiprocessor has a small amount of cache and a small controller, which it is used for accelerating the copying cache process of moving data from global memory onto that small cache. So when we say texture memory, what we're doing is actually caching global memory. So all of our data is stored in global, and then we're telling the GPU, hey, GPU, this is read-only, and I want you to start copying it to the GPU chip before we use it. You have to try to predict when I'm going to need it, and I want you to copy that information to my cache on the chip before I start my computation, and hope that when I'm doing my computation, each thread has access to that piece of information. So the amount of texture memory, the cache in each SM is very small. It doesn't mean that we don't have a lot of memory available for texture memory, because every texture memory variable is stored in global memory. And then we do cache copies to try to improve the performance. That's the only difference. So texture memory is cached, which means one thing. It means that the way we use texture memory must be very predictable to the compiler. 如果那个 compiler 没办法 predict 我们要怎么用那个 texture memory, 它没办法 cache the data. It can't copy the data we need to the GPU before we use it if it can't predict the access pattern for that data. So what does this mean? Well, let's just do it. If we're going to use texture memory, we need to remember that texture memory is just a different way of caching global memory. So we need to create data on the host and device, and then copy the information we want to the device first. 所以其实那个计算开始的时候就是跟一般的那个计算在 global memory 上完全一样。Copy the information to our device variable first. Then we need to bind it as a texture. We need to tell the computer, hey GPU, this section of memory, we're going to cache that. It's not going to change. It's cached. That means when I want to start using it, you need to start understanding when to move it across. Once it's bound, we can use this texture in our kernel computations. As I said before, there are like 30 functions available to us to use that texture as part of our computations. We will be using one of those techniques. All of the others assume that we are going to be performing operations across real CUDA textures, real GPU textures, but we're not playing games here. We're performing a calculation. 那个计算结束的时候, when we finish our computation, we copy the information back and we unbind the texture. We can tell the GPU, hey GPU, you no longer need to cache this section of memory. If someone here forgets to free global memory because I forgot to write free global memory on this flowchart, I'm going to be very upset. You know I'm just going to go over there and turn the machine on and off. But that means you guys are going to have to wait for me to take that walk. So, here's a flowchart. Let's look at some code. If you don't know what that means, you're in the wrong classroom. That too. Here is our texture type. Here is our variable type. Because this is a texture type variable, I've given it a name, tex. I should have called it dog. Anyway, tex is a texture variable. It is of type texture. What is all of that stuff? Well, we can put a whole lot of information inside a texture in CUDA. We can put integer data, half ints, characters, binary data. We can also put floats in. We cannot put doubles in. If we want to use doubles, we actually have a separate procedure. If you're interested in seeing my double texture float code, I can show you, but we're not going to test it in this course. We will be testing this. So, in this case, floating points. So the data I'm storing in my texture is of type float. 1, the dimensionality of our data. Textures are normally 2D, right? In games, we store textures in 2 dimensions before we map them onto our surfaces. We're not doing 2D in this class. Everything we do is 1D. So we have a 1D texture. So we write 1 there. This one here, CUDA read mode element type. Do not change that. Actually, that has to do with how we perform conversions upon CUDA texture texels. Does anyone here know what a texel is? No? Good. Don't change that variable. If you change that variable, you're going to start doing something to do with CUDA texels. And if you don't know what a CUDA texel is, then I would advise you not to touch it. And our name. So here we can say we're filling with floats, 1 dimension, not texels. We're not doing any texel conversion operations. Tex. Now, tex is the name of our texture that we're caching on global memory. We still need to have a global variable that holds the information that we want to use for our texture. So we still need dtext and htext. And our solution is going to be dA/HA. So we still need to use CUDA-malloc for dA. We still need to free that variable, but we need to cache it. When we want to access that, I dare someone in this classroom to do a Google search now for CUDA textures. Did it find this function? I bet it didn't. text1d fetch means we are going to search. You found it? Aha! That's the wrong. Oh, yeah, good. Don't use text1d. It has to be text1d fetch. So there are a number of functions we're using text1d fetch. We are going into that texture, and our array is a one-dimensional array in texture memory. We are pulling a float from that. And here's the name that we're pulling it from, and there is the index we are accessing. Do not try to use text1d or text2d or text3d or any of those other functions. Text1d fetch is good enough for us. Yeah. Keep going. Here is our main function. So our main function is pretty simple, straightforward. Step 1, we need to allocate the memory for our solution, HA and DA, and for our text, dtext and htext. So we use malloc for htext and HA, and CUDA-malloc for the other variables. Then we need to set what our value is for htext. Constant memory same deal. Pretty straightforward. You can have that variable as anything you like. After we've set htext, last time we used a CUDA memcopy to symbol for constant memory. This time we need to copy the information to dtext. So a conventional CUDA memcopy is in order using a CUDA memcopy hosted device. Once that information is on our GPU, we need to bind it. The engineers at NVIDIA don't have a good imagination. They called this function CUDA bind texture. 0 means, well, actually, for any texture, we can actually bind multiple pieces of information to the same section. If we want to bind different pieces of information to that same section of texture, we can use a different index to offset our access. This texture is only holding htext or dtext in this case, so we have a 0 offset. That's our index offset. Text, dtext, straightforward. Text is our texture type, dtext is our location in global memory, sizes that are not the size of the information we're binding. If you put htext there instead of dtext, it will compile, it will run. There will be no memory errors, there will be no errors of any kind. You will get 0. Your code will not run. Oh, it will run, sorry, but your answer will be wrong. So, don't do it. CUDA can't bind global memory, it can't cache host memory to the texture memory inside each of the SMPs. It needs to be device memory, otherwise it don't work. Once we've done this, we can run our test function, and again our test function, we access that information by using text1d fetch. Pretty straightforward. And text is the name of our texture variable, and I is going to be the index at which we access. We do need to check to make sure that I is less than n, otherwise we're trying to cache information which is not bound. Big trouble if you do that. So that's another good reason why we have if I is less than n here. Once that's done, we need to unbind it using unbind texture. Oh, I didn't write that down. Unbind texture text. CUDA memcopy to get HA and DA, or DA back from the device back into HA. Then we print HA to make sure our answer is correct, and we free everything. And we're done. Pretty straightforward. Like I say, this is a fantastic way of taking information which will not change and accelerating it by caching it. Now the good news is, see how it's bind and unbind? When I say texture memory can't change, all I mean is it can't change between here and here. It can't change between bind and unbind. But after you've unbound it, if the values change and you want to perform another calculation, but for that calculation the value doesn't change it, you can bind it again and unbind it. So we can use this technique to basically accelerate pretty much every single one of our finite volume calculations. Win-win. The performance of texture memory depends on a range of factors. Binding and unbinding is not free, so you do take time to do that. Data is still held in global memory, but it is cached, which means, basically, the threads need to be able to predict which sections of global memory that it wants to access. 如果那个compiler没办法 predict, then it can't, well, 应该是说, it requires multiple passes to fill the cache required for our calculation. If all of the threads access data which is located close together in our texture array, that means we can perform one copy into cache, and all the data we need is already in the cache. We don't have to perform extra copies, in which case it is very, very quick. 但是如果每个 thread 要再做一个另外一个 cache copy, then it's going to be very slow, 就是跟那个 global memory 一样慢。So, texture memory, worst case scenario, same speed as global. Best case scenario, many times faster, because we have cache effects. Application time. I've been waiting too long for this. Until now, all of our calculations have been baby calculations. We've been doing one-dimensional heat transfer. We did some two-dimensional heat transfer, that was easy. And we did one-dimensional advection diffusion equations. Let's do a real problem. Shallow water equations. Someone put a message on Facebook about their first class in GPU, and I read that some other student who took my class before actually wrote a message about shallow water equations, and I thought, that's a good idea. I'll put shallow water equations back in the class. So thank you very much, Facebook. You inspire me. Shallow water equations. We're going to solve the height average Navier-Stokes equations in one dimension. So we have a dam. We have 10 meters of water here, 1 meter of water here, over 100 meters with the dam in the middle. At time equals 0, I'm going to take away the wall, like magic. It's gone. Like Harry Potter will use his wand to make the dam disappear. In reality, the dam will break gradually. But in this case, we're going to make the dam disappear instantaneously. When the dam disappears, what do you think this water is going to do? Rush that way. It's going to charge downstream. There's going to be a hydraulic jump where we see basically a wave of water, a wall of water charging downstream, after which we see the flow will be moving, and we'll see after that an expansion back up to 10 meters. How do we solve these? Here are our equations. Now these are special equations because until now, all of our PDEs have had one conserved quantity. These PDEs have two conserved quantities. Actually, these are a delightful group. And if you can solve these, then you can probably solve the Euler equations and then the Navier-Stokes equations after this. So there's a reason I teach you guys these equations, because they're very useful. So, in this case, standard form. This we've seen before. But U is a vector. This is our water height, the water depth. This here is basically the momentum, where U is the speed. So water depth times the water speed and the water depth. Our flux of water is, well, this is, remember from fluid mechanics, m dot equals rho AV. This is a flux per unit area. That's our height, that's like rho, that's velocity. So if you've got height of n and that much speed, then the flux of water across any piece of space or surface in space is going to be that per unit area. Momentum. That is the real momentum, and this here is a pressure. If you've got n meters of water, you guys might remember thermodynamics. If that's the depth of the water, the average pressure that depth of water will exert on its neighbors is the pressure at halfway. At halfway, the pressure is NGH on 2, and we need to multiply that by the area over which it acts, which is that. Hang on, that's G, that's N, and multiply that by the area, and we get a half G. Oh my god, what am I doing? rho G, my golly gosh, that. Forgetting rho, we get this. You'll see I've missed rho here. We'll talk about this in a little bit perhaps. So we'll use these equations, that's fine and dandy. How are we going to solve it? The system is hyperbolic. We can't use central differences to solve this. That PDE doesn't work, it blows up, unfortunately. We can use an upwind scheme, but I've decided in this case we're going to use a very, very simple technique called SHLL. SHLL basically computes the flux across each surface as a sum of split fluxes. So all the equations are here. And for this calculation method, we need to know what the Froude number is. That is basically equivalent to the Mach number for a gas. So the Mach number for a gas is important for us in understanding supercritical flow. Same deal. Froude number tells us when the flow is supercritical. U is a speed, A is a propagation speed, which is proportional to root G n eta. Oh, I've given you the whole code. So this is a CPU code. We define our problem size up here. We've got U1, U2, U1, U2 nu. Remember, we have two PDs we're solving together, each with two U's. We have conserved quantity 1, which is that water depth. Conserved quantity 2 is the momentum. We need to solve for both of these. So we're going to need U1, U2, and we need U1 nu, U2 nu as well. We have four fluxes essentially. Each cell is going to need Fi plus a half and Fi minus a half. Fi plus a half is made up of Fi plus and Fi plus 1 minus. So we have minus fluxes and plus fluxes, minus fluxes and plus fluxes. If we can work out the minus fluxes and plus fluxes in every cell, then we can use them to create or calculate Fi plus half, Fi minus half, and then we can use those to evolve the flow. So our new conserved quantity is the old one minus that stuff. So everyone has one of these functions already, am I right? Allocate memory. Free memory. If you don't have one of these functions by now, I'm going to kill you. Compute fluxes. This function is going to compute our split fluxes for us. Compute U is where we compute the new U using those split fluxes. Update U is where we copy the new U over the old U, and we're done. Init is our initial condition. Save result saves the data to file. Here is our main function. Allocate memory, initiate our problem. Take a large number of steps. Save the results and free memory. If we do this on GPU, we have some extra steps. We need to copy information to the GPU and then copy it back. I did not show you how to allocate memory or free it. By now you should know how to use malloc. Pretty straightforward. In it, we're using the initial conditions we see here. If our value for location is less than halfway along our problem, then we want the water depth to be 10 meters deep. Otherwise it's 1 meter deep. So we say this here. Once we're done, we save results using a file pointer. You can use a file stream if you want. Our compute fluxes compute Fp and Fm. Here are our equations for Fp and Fm, our split fluxes, F plus and F minus. F plus, this chi is basically the critical number, which is the Froude number here. So chi here and there are the critical numbers. So in each cell, what do we need to do? We have a for loop here. Hey, 我们写 GPU 的软体的时候，这个 for 会变成一个 if, because every thread它会处理一个 cell. We calculate the velocity first. Calculate A, which is our propagation speed, then our Froude. Then we calculate the flux functions. We need the flux vectors here and there. Then we can calculate Fp and Fm. Once we've got Fp and Fm, we can calculate FL and FR, which is the net fluxes across each surface on the left and right hand side. If we're on the leftmost, we're going to have special boundary conditions. Right is also special boundary conditions. Otherwise, FL is basically F plus from I minus 1 plus Fm and I. FR is basically F plus and I plus Fm and I plus 1. Everything is here. All you guys need to do is copy my code. pretty easy job. Let's see what happens. I've given you the results. After listening to you guys with the advection diffusion problem with the smoke simulation, I'm throwing you a bone. This is what your code should give you. This is the water height after 8 seconds. 4 seconds? 8 seconds. 4 seconds. Yep. This is the leftmost part of the domain. It is decreasing down. Here we have our post-hydraulic jump. Here's our jump. So on the right-hand side, the wall of water has not reached this point yet after 4 seconds. But after 4 seconds, it's traveled 40 meters. It's traveling at 10 meters per second. That's a pretty fast wave. But it means that if you're the fastest man in the world, you can actually run away from this wave of water and survive. The rest of us fatzos are going to die. So we have a hydraulic jump here. This is equivalent to a shock wave in Navier-Stokes and Euler flows. So the water level instantaneously jumps up. This is a flow speed. Flow speed is 0, then it jumps up to about 7 or 8. 7, yep. And then it decelerates as it goes down as the expansion is completed. You have the result. This is what the answer looks like. Your mission today, write the GPU version of that code. You can choose, if you want to use shared memory, texture memory, or constant memory in your solution if you wish. At the end of the class, I'm going to show you my solution. But we already know what the answer looks like. That. So, your mission is quite simple. Copy my code. I would personally start with the C++ code to make sure that I get the right answer before I start writing a GPU code. Now this might be a new concept to you guys because every time I ask students to do this, they skip the CPU code, they just jump straight to the GPU code. I would advise you make sure your CPU code works first. If your CPU code doesn't work, then your GPU code is definitely not going to work. So do CPU first. See if you can use shared memory or texture memory. It's just for fun. Students who use texture memory will get bonus points for the subject. That basically means you'll get a higher score at the end of the semester. So if you can show me this code that uses texture memory, I'll give you 2% extra on your final score for the subject. Your call. Show me when you're done. Now, you guys have to have some self-control here. Because after this, don't look at this already. Here is my GPU code. You should try to write your GPU code first. Now, when your GPU code does not work and you're ready to break down and start crying on the floor, then you can look at my GPU code. Don't look at my GPU code until you've tried to write your own. Because this is the kind of problem that you'll get on your mid-semester exam. Your mid-semester exam next week, I'm going to give you a code and you are going to GPUize it. So it is good practice. So when I'm showing, everyone should be shutting their eyes right now while I'm going through this. Don't look at this screen. Get to work. Good luck.